Hi there. Today we'll look at Deberta, Decoding Enhanced Bert with Disentangled Attention by Pengcheng He, Xiaodong Liu, Jianfeng Gao, and Waiju Chen of Microsoft. This paper is an improvement on Bert, the language model, and the Roberta variant of it. Specifically, it suggests two improvements, namely, first is this disentangled attention, where they disentangle positional information and content information of the individual tokens in the attention mechanism. And the second improvement kind of results from the first improvement as this decoding enhanced decoder, enhanced decoder, where because they only use relative positional information in the transformer part of the model, they have to re-feed the absolute positional information at the end, which gives them another bit of improvement. Altogether with this, they reach state-of-the-art in various NLP tasks, and this model, Deberta, is now available in Hugging Face for you to download for all of your NLP needs. So we're going to go through the paper and look at the two improvements and what they give. Let's see if that's relevant. As always, if you like content like this, don't hesitate to share it out to all of your friends and leave a like and a comment. I still read all the comments, so give me your opinion. And please also give me your opinions on the new recording setup. There should be a title somewhere here, a picture somewhere here. I absolutely want to hear feedback because I have no idea what I'm doing. So, yeah. All right, let's dive in. Deberta or Deberta. I don't know. I think it's Deberta because it's from Decoding Enhanced. Deberta is a new model architecture, they say here. We propose a new model architecture, Deberta, Decoding Enhanced Bert with Disentangled Attention, that improves the Bert and Roberta models using two novel techniques. The first is the disentangled attention mechanism, where each word is represented using two vectors that encode its content and position respectively, and the attention weights among the words are computed using disentangled matrices on their contents and relative positions respectively. Okay, we'll look at that first. So what they mean is when you have a multi-head attention layer, what we want to do is we want to transform one sequence of tokens, of token representations, into the next sequence of token representations. Now, usually, every token, let's say these are our tokens, and this could be a sentence in a language like I am hungry. And here is like this classification token that we always add when we train Bert. Every one of these tokens is represented by a vector. Like this is a vector, this is a vector, it has many entries, this is a vector. Some of the vectors are thicker than others. I mean, that's just this one just hasn't eaten enough. So every one of these tokens is represented by a vector, and what a multi-head attention layer does is it simply transforms this via means of the attention mechanism into a series of vectors again. So we put in a series of vectors and we end up with another series of vectors. If you want to know what a multi-head attention does in detail, please go look at my video, Attention is All You Need, where that's explained. Specifically, it is sort of an information routing algorithm that sees how information needs to be routed from tokens to tokens using queries, keys, values, and so on. If you haven't seen the video, it's a beautiful mechanism, but I'm not going to explain it again right here. I'm sorry. All right. So in this, what you usually do is you transform vectors into vectors. And because of how the multi-head attention mechanism works, the mechanism has no way to discern where in a sentence, for example, a given token is. So it cannot differentiate between this sentence here and the sentence, am I hungry? If it's just multi-head attention, it's just not possible for it because it treats the incoming sentence as like a bag of words, which is not the case in, for example, a recurrent neural network. So a recurrent neural network would go one by one over these word representations, and it has kind of a mechanism to see what a sequence is. However, multi-head attention doesn't. So what people usually do is they augment these representations with position encodings. So that's at the beginning, where you might ask, where do these vectors come from? Of course, they come from the last layer, but the very first vectors you put in come from a table. And these are your classic word vectors. So at some point, you have a big table, and the big table has your entire vocabulary in it. So every word in the language that you consider. So there's I, and there's am, and there is you, and there is apple, and there is hungry, and there is even this CLS token. All of them have a table entry, and all of them have a vector associated with them. Now, these vectors are trainable, so the neural network can decide itself what goes into these vectors, but every word has a fixed vector in there. And in the very first layer, because you don't have a last layer to draw from, you simply look at what token it is. You go to the table right here. You retrieve this vector, and you put it here, and that's your start. And then you transform up the layers, of course, every time from the last layer. But at the beginning, you have embeddings. Now, the same thing you do for positions, okay? So you also have a second table, usually. And the original transformer paper, by the way, these were fixed vectors. But nowadays, I think most of them are also trained. So you label the positions. So that's position 1, that's position 2, 3, and 4. So for every position, 2, 3, 4, and maybe you have also 5 and 6, there is a maximum length. But right now we consider sentences of length 3 with a CLS token appended. So these are length 4. So every position also has a vector. And I'm going to actually draw these vectors in this color. So every position has a vector, irrespective of what word there is, okay? Right now, we just have vectors for words, irrespective of where they are, and we have vectors of positions, irrespective of what words there are. And what you do is, same, you look at what position is here, you go to the table, you retrieve that embedding, and you somehow also put it here. Now, I've made a bit of a mess here with this thing, sorry. So how do you, now you have 2 vectors all of a sudden per word. So you have one that is a position, and you have one that is the kind of the word itself, that represents the word itself. And the neural network, it needs both in order to understand the sentence, right? If every word has these 2 vectors at the beginning, now it can understand, aha, this is the word I that is at the beginning of the sentence, so it's probably the subject of a sentence. However, if the word am was at the beginning, it could be, oh, it's probably a question because it starts with a verb, like am I hungry? Okay, and it can also evaluate the relative distances of things to each other and so on. So given this information, the neural network has all the tools it sort of needs to understand that sentence as a sequence. Now, what you have basically 2 ways of combining the 2 things. First of all, you can concatenate them, which means that, I'm going to do it in this, you just put, no, that's terrible. You just put the, I'm not too skilled yet with this new thing. You put this on top here, imagine this is the same length, and you just concatenate the vector. So now the vector is longer. Of course, that also increases your dimensionality, computational issues, and so on. So what a lot of people do is they simply, line them up if they're the same size, and they add them together element-wise. And in the worst case, the neural network now can decide, because both of these are trained, right? So the neural network can absolutely decide that, in the top part here, it simply learns a bunch of zeros, and in the bottom part here, it simply learns a bunch of zeros here. So essentially, it's a concatenation. That's the worst case. In the best case, the neural network can actually do some kind of information combining already in this addition step down here. Okay, so you give both encodings to the neural network as a single vector, right? So what goes into the multi-head attention mechanism is a single vector. This paper says that is not ideal because the positions are too much mixed with the signal of the content of the words, and we'd rather have this in a disentangled representation such that the network can sort of reason about the words in one line and it can reason about the position of the words in another line. So their goal is to disentangle these two vectors and basically design a new attention mechanism that always treats the content and the position as separate things. So the new attention mechanism they propose is right here. Of course, they can't stay separate, right? But they can be disentangled through the layers. So their new algorithm sort of is here. The way they obtain the attention matrix is due to the following thing. So how do you usually obtain the attention matrix? You have your input, X here, this is your sequence, and you produce two values from it, Q and K. So these are matrices. So if X is a sequence, then every single sequence element emits one key, which is a vector, right? One key. And then every single one also emits one query. So like this. And the key the key is supposed to say what information is this token about, and the query is kind of supposed to say what information does it request from other tokens. So now you route the information wherever the inner products line up. For example, probably this thing would be routed here and so on. It's not a hard routing, it's a soft routing. So by transforming X by linear transformations into keys and queries, you obtain your attention matrix by multiplying together queries and keys, such that you have sort of the inner product between each of these vectors. And this is quadratic, and this is the big bottleneck in transformers. But you have the inner product between each of the two. You get a giant matrix, and the giant matrix basically says how much does token 2 attend to token 3. That's the position 2, 3 of that matrix. And that element is going to be the inner product of the query of token 2 with the key of token 3. So that's how you do the attention matrix. And these vectors right here, if you do regular Bert, they're always everything at the same time. So you feed content and position somewhere down the layers. You feed that in, you add it together, and the network is supposed to figure out itself how to use these two pieces of information. This paper says, no, wait, we can do better. What we can do is, for us, each sequence element, it does not only produce one key and one query, we think it should be made up of two vectors. So each of these things has two different components. One is this kind of H component, which is the content information, and one is the P component, which is the positional information. So here, how should token I attend to token J? They say, well, it's going to be the same thing. It's going to be the inner product between this is the query of token I, and this is the key of token J. Okay. However, now the queries and keys are made up of two different parts. One is the content part, one is the position part, and the position, as you can see, maybe, is J conditioned on I. The position is going to be a relative positioning. So if you have your sequence right here, what each token would do is it would emit one vector. It would emit one vector that is the content of the token, like before, and then another vector would come in from the position. So the same we did at the beginning, but now in each layer, this positional information comes in, irrespective of what word there is, right? Irrespective of what word is in the position gets an encoding right here. And then the interesting thing is we don't add the two together. We treat them actually separately. So here the keys are 2 vectors and the queries are also 2 vectors. So I'm just going to draw one up here. So the query is going to be a vector and the query for the position is also going to be a vector. And that also, it depends only on the position and not on the incoming signal. Okay. So now, how do we route information? Now, we have 4 different routings. First, we only consider dark blue. So this is kind of the classic attention, right? This and this, they match really well, so that goes here. That one probably doesn't go there, and so on. But then we also, so this is what they call content to content routing. But then we also have content to position, position to content, and position to position routing. And in all of these, so for example, in content to position, now I'm sure there's a 50-50 chance I'm gonna mix this up, and I'm sure I'm going to, but in content to position, what we're going to do is we're going to look at this vector right here, which is the content vector of the query that is produced from the token, right? The content is produced from the token, and we're going to attend to the position vector of the keys. So we're going to attend to the light blue things. So essentially, this part is like the classic attention part. It is, I am the word am. I'm requesting all information from all the nouns in the sentence because I'm a verb and I would like to know who are the nouns in the sentence. Okay. Then the content to position encodings is, I am the verb am. I would like to know what is around me. The positions are relative positions. So I can request the vector for, the +1 position of me or the +2. So the word can attend to its surroundings. So given that it's the word am, it might be particularly interested. Maybe it has already figured out it's not a question, right? From the previous layers. So it's particularly interested in what's before it. So because, am, actually it probably isn't particularly interesting because it's always going to be I. So actually maybe it's exactly a counterexample where it wouldn't want information from there. But it can sort of attend, it can say, I want to attend to things after myself because I already have figured out that before me must be an I. I want to attend to things after me, like one position after me, what's right after me, what's 2 words after me, and so on. Position to content is exactly the opposite. It is saying, so the token can say, well, I am in position +4 to, what kind of information do I want to send to things that are 4 away from me, right? Irrespective of what the content is. So here we simply consider what position is the token with respect to its neighbors and what kind of information does it want to aggregate from each of the words. It's a bit weird, right? So it says like I am in position, a word that is 2 words after me. What kind of information do I want to get from it? And since it's attending to content, that can be dependent on what word there is, but not its position. And then position to position is simply, well, what kind of information do I in position 3 want to send to something in position 7, which would be useful, but this is relative position encoding, which simply means I am always kind of in the middle, and so this isn't really helpful, so they decide to leave this away. So we end up with the 3 different attention mechanisms, so to say. We end up, so there's this one, and there's this one, okay? Corresponding to the 3 out of 4 different ways we can combine the dark blue and the light blue keys and queries. Now, you can see right here, that's what they do. And their final attention matrix is simply the addition of all of those together. So we construct one attention from like the classic attention. We construct one attention that is content to position. We construct one attention that is position to content, and we construct one that is position to position, but then we leave it away because we deal with relative position. So it would sort of be the same for every token, and that's not particularly helpful. I'm going to repeat it again. The H information contains actual signal from the last layer, while the P has no idea about the signal. It simply contains information about the position of the tokens. Okay? So you can decide to send information to a word that's 2 positions ahead of you, or to request information from a word that's 3 positions behind you, depending on what word you yourself are. Okay? So that's the content to position and position to content attention. These things are all added together, and that makes up the final attention matrix. So a final entry in the attention matrix could be influenced by multiple ones of them. It could say, you know, I'm the word am, I'm in position 2. I request a lot of information from other nouns. If any noun is here, I want information, but I also want information from things that are 1 or 2 positions ahead of me. So that is, and you know, since I'm the word am, and also since I'm in position number 2, I am very interested to know what the subject of the sentence is. Now we have all of it, okay? All right, and the rest is just like classic attention, okay? Now you simply, so these P and H matrices are obtained by, the queries and the keys for this are obtained by linear transformation. So you see, this is the incoming signal. You send it through a linear transformation to obtain the queries, and you also send it through a linear transformation to obtain the keys. So the H is the same, but these matrices here, these are learned weights to produce queries and keys, and then you multiply them together. That defines your attention matrix. You run that through a softmax to make a distribution out of each row, and then you multiply together with the values. So this part here is kind of like the routing table, and the values are the information to be routed. The values are obtained from this input signal. As we said, we're going to amend that by, so this over here is the classic queries, keys, and values. Sorry. That's too much. The classic queries, keys, and values. And then we augment that by 2 new. So there is the queries and the keys for the position. And you can see that the difference here is that, again, it's learned weights, but now there is this P thing right here. And the P is positional encodings, and that comes exactly out of this table we saw up here. So the positional encodings come from this. So, and it's important to see that this here is H and this is the P values, but this is only H0, right? H is actually transformed to H1 by the transformer, the first layer, to H2 by the second layer, and so on. The P always stays the same. So you would feed the P into this layer, and you would feed it again into this layer, and you would feed it again into this layer. So you can see it's only positional information. It's not content information. And by feeding the position each time and doing this in this disentangled way, the model can sort of keep the content and position information separate. I actually think it doesn't really keep the information separate because, you know, after layer 1, you certainly have position information in your H, right? You can see that from this path here, from the actually feeding position information into the transformer layer, H1 is already going to be a conglomerate of H0, which is pure content, plus the position somehow. This plus is not a real addition, but somehow the information is intermingled there. And if we weren't to feed in these things right here, it would just be like the classic Bert, right? What they criticize. Now, by continuously feeding the positional information, that is one advantage. You can actually do that with Bert. You can just add the position information each time. I'm not sure if that would work super well, but you can do that. Just gives the model a bit more side information to work with. And then by keeping it separate, yeah, as I said, I'm not sure it's actually separate. It's just that you keep feeding in position information layer after layer, therefore giving the model sort of more information every time it makes a transformation, because otherwise it would have to carry through the position information through all the layers just from the very first layer. Okay? So in this mechanism, you can see it's true that the position encoding is kept separate because it comes in fresh every layer. But I don't see that the content certainly has position information in it from the last layer. Like, I hope you can see that. So as I said, they do relative position encoding. What does that mean? So that means that the position encoding depends on where you look from. So what I've drawn at the beginning, like this here, this isn't entirely correct. You have to look at each token individually. So for this middle token here, for example, the positions look like this. They look like -2, -1, 0, 1, 2. And you'd have kind of a table, not with absolute positions, but you'd actually have a table with -2, -1, 0, 1, +1, +2, and so on. And you would retrieve those vectors. And then when you consider the next vector, this one right here, it would look different. It would, right, this would be 0, this -1, -2, and so on. So they do two things. First of all, they truncate at some point. They simply say, well, our context window is 2, so instead of going -3 here, we simply keep it at -2. So everything beyond -2 gets also the vector for -2. So that vector here is going to be just plugged into here and into here for this token, right? And for this token, for the previous token, it is only going to be plugged here and nowhere else. There are ways to efficiently implement this, and that's this algorithm right here. Don't want to go too much into it, but just so you're aware, you don't have to consider each token really individually during its attention. That would be prohibitively expensive. So you can do one big matrix multiply and then sort of pick and choose together from your from the matrix that results, especially with this truncation. This is this algorithm. So they call it efficient implementation. All right, so that is this position enhanced or disentangled information. Why is it disentangled? Again, because in every layer they have a side input. This piece right here is the side input that they sort of feed on top of this information, and they specifically construct the attention matrix out of the three things, right? It's almost like two contributions. The one contribution is, hey, let's feed in position information in each layer, and I think that has been tried before. That's pretty simple. But then the second thing is that we don't simply add the two vectors when we input it into the attention, but we're going to construct basically three attention matrices and then add those together once we determine the inner products between each of those, okay? So this is one of the improvements, and that already helps a lot, but then they run into a problem. And this is not necessarily a problem with their method, but this is a problem in general when you use relative position encodings. So they say, given a sentence, a new store opened beside a new mall, right? That's a sentence. The words store and mall are masked. So let's say you do this masked language model pre-training, right? You mask out the words store and mall and you ask the model to reconstruct them. Using only the local context, e.g. relative position and surrounding words, is insufficient for the model to distinguish store and mall in this sentence, since both follow the word new with the same relative positions. So from the word new, you know, relatively, it's always +1. Oopsie. It's +1 to this word. So the model cannot distinguish the two. So there is a need for absolute position encodings, because if you had absolute position encodings, you could maybe make sense. Though since you could figure out like store is probably kind of a smaller thing and mall is kind of a bigger thing. So it's more likely that the store opened beside the new mall than the mall opened beside the new store. Okay, so that means we need absolute position encodings or something like this, right? And especially we could have relative position encodings, but if this is a very long sentence and we truncate them somewhere, again, these two things are not in range of one another, and they're not going to know how far they are apart, and each one by itself is just +1 apart. So how do we solve the problem? We feed in absolute position encodings. However, that's exactly what they criticize. They say, no, relative position encodings are much better than absolute for learning. And that's kind of the same reasoning why a convolution is better than a fully connected layer, because you kind of slide the transformation over and it's simply data relative to each other. So relative positioning makes a lot of sense when every word can do computation not based on where exactly it is in the sentence, but how it is in relation to other words. Otherwise, if you have absolute position encodings, what you would have to do is you would have to say, well, if I'm the word am and I'm in position 2, I need to learn to attend to position 3. However, if I'm the word am and I'm in position 3, I need to learn to attend to position 4. And if I'm in position 4, I need to learn to attend in position 5. These are all different things you need to learn. However, if you have relative encoding, what you can do is you can simply say, I want to attend to the word that's right after me. Easy. But we do need absolute position encoding for some things, namely disambiguate between tasks like this. So they feed in absolute position information, but instead of doing it at the beginning, they do it at the end. So at the beginning, we have the word vectors, right? They go in here. And then we have position information. 1, 2, 3, 4, 5. We have that at every single layer of the transformer. We feed it in again and again and again. We feed in the same p vectors, okay? They have different of these of these transformations in each layer. So the actual transformation that makes the keys and the values, the keys and the queries of the positional information are different, but the vectors are the same every time. And then at the very top, so these are p relative. So this is, I mixed up. This is this -2, -1, 0, 1, 2 for the middle token. And then at the end, we're going to feed in absolute position encodings. So here we have, let's start at 1. Let's be good MATLAB people. Here we have 1, 2, 3, 4, 5 that we're going to now combine with the vectors that come out of here. So the reasoning is, they say there are two methods of incorporating absolute position. The Bert model incorporates absolute position in the input layer. In Deberta, we incorporate them right after all the transformer layers, but before the softmax layer for masked token prediction, as shown in figure 2. I've looked at figure 2. It's not really helpful, honestly. So that is this figure in the appendix, where they say, okay, so in the Bert you have the absolute position encoding somewhere down here. It goes through all the transformer layers, and then you have this classification layer at the top that does the language model decoding. However, in their model, what you'd have is you'd have all the transformer layers here, down here, and then you have the absolute position encodings that come in through the side here, and kind of the last transformer layer now has access to these absolute layers, or the last n. I think n in their case is 2 or 1 or 2. So in the last layer, or the last layers, now the transformer has access to the absolute positions, and before it's just relative position at each step. And they reason that that helps because the transformer part learns to deal with relative positions. Okay, in this way, they say here, Deberta captures the relative positions in all the transformer layers and only uses the absolute positions as complementary information when decoding the masked words. Thus, we call Deberta's decoding component an enhanced masked decoder. And they compare the two, and they observe that EMD works much better. So feeding absolute positions at the end works better than feeding them at the beginning. Okay. We conjecture that the early incorporation of absolute positions used by Bert might undesirably hamper the model from learning sufficient information of relative position. In addition, EMD also enables us to introduce other useful information in addition to positions, yada, yada, yada. We leave it for future work. So they say you could also feed in other information. I guess that's the case in every single neural network ever. Yeah, but the point is they feed in the absolute position at the end, and their conjecture, so I'm not sure, I'm not a fan of this. Here, this is like saying, okay, if we only feed it in at the end, right here, this is position absolute, then we sort of limit the model. Like right now, the model has the same information as it had before, as if we were to feed it at the beginning, but we sort of limit it to only one layer of transformation. So all it can do is sort of have kind of a little linear transformation in there. And so if we don't feed that in here, whereas we do feed it in, the model can use it any way it wants. And that's just not a good enough reason for me. So I think, regularization has its place, bottleneck layer has its place, and so on, restricting the capacity and so on. But I'm not a fan of hampering the model in this way, kind of restricting it. And just because it makes your number better, there's not really a reason why the same information should be worse if you give the model more steps to compute with. If you feed it in at the beginning, technically, if you train the model correctly, it should learn to use that information in at least as good a way as if you feed it in at the end, right? At least. That tells me that the model, that we haven't really figured out how to train these models correctly yet with regards to positional encodings. And again, I'm not a fan of simply saying, well, we only feed it in at the end, because then the question immediately is, well, how many layers at the end, how many layers at the beginning, or when is it too it's just, yeah, I don't think it makes a lot of sense to simply give the model information but not let it do its best with that information unless you have a specific kind of reasoning why. This is just not good enough for me here. Not a criticism of the, obviously it's better, like they observe, like, all the information, all the arguments can be invalidated by, but it's better, right? That's deep learning. So yeah, all respect for them for trying it out and actually realizing it's better. Pretty cool. So they also do scale invariant fine tuning, where if they fine tune, which is where you take kind of this model you trained with masked language modeling and then you fine tune it to NLP tasks, they have a bunch of tricks there, like virtual adversarial training and normalizing the embeddings before they do that, and that apparently helps a lot. But they also say they leave the comprehensive study of this for future work. For now, they just want to get the good number, which is understandable because you get published. All right, so here you can see, actually we can skip most of the tables. They are better in language modeling too, which is interesting. So they can do kind of Bert style denoising, but in classification you can also do actually autoregressive language model, which is pretty cool. So here they do an ablation study of the different components, where they remove this enhanced decoder, and one time they remove the content to position encodings, attention mechanism, and one time they reduce the position to content attention mechanism. And in the table, it is sort of a wash. It depends on the task of how you look at, but each of the components here gets you some kind of a benefit or a hit when you take it away. So yeah, it's not really clear that one of the components gives you all the boost. The combination of them is obviously the best, and it's really cool when papers do these kinds of ablations rather than just throw a bunch of stuff at you and it's on you to figure out which of that stuff is important. They compare it to Roberta in terms of training, of accuracy after training. So how much do you need pre-training for a fine-tuning, and the Deberta, as you can see in these graphs, outperforms Roberta. So potentially you need less pre-training steps to reach the same accuracy in a fine-tuning task, which is cool. Also means that if you train for longer, you reach, or if you train for the same amount of time, you reach a higher accuracy. And now for, you know, their big thing they build, they scale it up, and they have a bunch of tricks here. And, you know, pretty cool, they scale it up. I just want to highlight one trick. We optimize the model architecture as follows. First, we share the projection matrices of relative position embeddings. Okay, so they share the projection matrices of the relative position embeddings with each other. Okay, so they share the position matrices with the content matrices. So now, instead of, for example, so here is the query of the content, the key of the content. Here is the query of the projection and the key of the, position. My battery is soon over. I have to speed up. So the content right here and the position right here give rise to these matrices by means of these learned weights, right? So here is WC, here is WKC, that's the matrix that generates the queries from the content, that generates the keys from the content, the matrix that generates the queries from the position, and the matrix that generates the keys from the position. So if you now want to share this and that, and also you want to share this and that. So and at the end they are added, right? So you multiply these things and then they are added. And in my mind, honestly, what that results in, because before, let's just see. So before you had something like, if we simply multiply query times key transposed for the context side, that would give you sort of context WQ, and now we share them, so we don't care about C and P anymore. WK transposed, K transposed, and of course context, this transposed, and now we add them to something else, and let's just say we have these position to position encodings that they leave away, but you know, we're going to consider them because it's easiest. So it's position WQ, WK, transposed, position transposed. You know, if these matrices are shared, this simply ends up to being the addition of the position and content times these two matrices times this. So, and this is just like the old school attention mechanism. Now I see there's these cross terms and maybe they influence something, but it gets closer and closer back to the old mechanism where you simply add the encodings and don't consider them in a disentangled way, right? If you like share the matrices of the disentangled representations, it simply refers back to as if you were to feed the position in each layer of a traditional transformer. So yeah, I'm not sure how much really the disentanglement is super important, or whether or not it's just, you know, more important that this positional information is actually available at each step. But, you know, I might be wrong here with the cross terms. I haven't actually looked entirely at that. So that's the paper. They have kind of a discussion, a depiction of attention matrices down here, where they show that their model, you know, does something kind of different from other models in terms of where it attends. And it has less of these global attention patterns like Roberta has right here. except for the very first one, which is the CLS vector, which makes sense and otherwise has a rather diagonal attention matrix. So that's, it's pretty sensible, though you can also make the case that sometimes there are just really important words in a sentence that everything should attend to. I don't know, but it is state of the art and it is a cool algorithm and is worth considering if you build your next model. All right, with that, I thank you for listening. Subscribe if you haven't. I'll see you next time. Bye-bye.